Hello, everyone. Today, I'm going to talk about a technique that might be useful if you ever train a classification solution. And that technique is changing the probability threshold. Okay. The first thing I want you to know is in what situations changing the probability threshold is a valid option. Right? Well, when we are obtaining a classification solution and we have unbalanced data, we usually need to do something to improve performance, okay? And just remember that unbalanced data means that, let's say we have two classes. So let's say in the classification scenario that we have, there are two classes, 0 and 1, the negative class and the positive class. Unbalanced data means that one of the classes, usually the negative class, is much more prevalent or frequent than the positive class. Okay, that's unbalanced data. When you have unbalanced data, usually you don't get a good performance initially, and you need to do something to improve it. Okay. Two common things to do are you can oversample the minority class or undersample the majority class or both. So you can do both things simultaneously. So you can oversample the minority class and undersample the majority class. That could help. Actually, that usually helps to improve performance when we have unbalanced data. But a second solution, different from the first one, is changing the probability threshold. Okay, and that's what this video is about. Okay, how to change the probability threshold, and then to show you that doing that actually could work. Okay, now let's try to understand how the probability threshold is used to make predictions in a classification setting. All right, so remember, guys, that in a classification setting with two classes, okay, and that's kind of the most common classification setting. So we have two classes, 0 and 1, negative, positive. Okay. The model predicts the target to be one, the target variable to be one, if the predicted probability returned by the model is greater than 0.5. Otherwise, the target is predicted to be zero. Okay. Now, here we have two components. So the predicted probability, like in this inequality, notice that we have two components. The predicted probability returned by the model, and that's something that we can retrieve, okay? We can always retrieve that. And this 0.5. That 0.5 is the probability threshold. And zero point 0.5 is the most widely used probability threshold. Is actually the default probability threshold, and it's actually the threshold that you want to use if you want to maximize the overall accuracy. So if your goal in your classification solution is to maximize the overall accuracy, you should use threshold 0.5. The issue is that sometimes you don't want to maximize only the overall accuracy. Sometimes you want to get what they call a very good also class-specific performance, meaning that you want a good overall accuracy, but you also want a good accuracy for the zero class specifically, and also a good accuracy for the one class. In other words, sometimes you want overall accuracy to be good, but also a good specificity and a good sensitivity. Specificity is the accuracy for the zero class. Sensitivity is the accuracy for the one class. Okay. So if that is the case, so if you want to get not only a good overall accuracy, but also class-specific performance, sometimes it's better to use a different threshold, okay? And that's what I'm going to show you in this video, okay? I prepare a Python notebook to this video, and let's jump into a notebook so that I can illustrate how to change the probability threshold and in the effect that it has in performance, okay? All right, let's go ahead and do that right now. All right, this is the notebook I prepare. I'm going to share a link to this notebook in the video description so you can have access to the notebook. All right, so let's start by importing all the libraries and functions that I'm going to use in this video, and everything that I am importing here, I will use in this video, all right, somewhat. Okay, so let's start by this, numpy pandas, matplotlib, and then a bunch of scikit-learn functions, okay? So I'm gonna use scikit-learn to illustrate how to change the probability threshold for one specific classification solution. So I'm kind of importing a bunch of libraries from scikit-learn. All right, perfect. So the data I'm going to use is the default data set. I have this data set stored in a CSV file locally. So what I'm going to do is I'm going to upload it to the Colab notebook. And then once loaded, I can read it as a data frame. So from the CSV file, I can create a data frame, okay? But let's go ahead and upload it first, okay? So you go to the Files tab, and then here you can upload files to the Colab notebook, and that's the default data set. By the way, I will also share a link to the data set in the video description, okay? There you have it. So now you have the CSV file stored in your Colab notebook. So we can go ahead and close this. All right, so first you define the path in Colab to that file. Okay, that's the path in Colab to that file. And then using that path, you can apply the read underscore CSV function to read the CSV file into a data frame. Okay, I title the data frame default data frame. And let's take a look at the default data frame. There you have it. So the default data frame has 10,000 rows and 4 columns. This is data about 10,000 people, and for each person, they recorded or stored 4 pieces of information. So the default status of the person, this is whether the person defaulted or not on her credit card balance. Okay, so the student status of the person, so whether the person was a student or not, the credit card balance of the person, and the income. Okay, so it's kind of financial information. Okay. And the target here is default, okay? That's the target variable to predict. So we want to obtain a classification solution to predict whether the person will default on her credit card balance or not, okay? All right, and then we have 3 features to that, okay? Student balance and income. Okay, so let's do a little bit of data exploration and preparation. The first thing I want to do is, by the way, guys, so I didn't want to spend time writing the code live as I was doing the video, so I already included all the code. Okay, so to save time, and I'm gonna explain the code, but yeah, I just wanna to have that already here. Okay. Anyway, so let me start by exploring the target variable, the default column, okay? And for that, I'm gonna apply value count, and I'm gonna normalize through just to get, instead of the count, the percentage. So I'm gonna get a count of each category of default, and but then I'm transforming that into proportions, okay? By using normalize through. Anyway, so when we take a look at that, we see that, well, default has 2 categories, no and yes. These are the classes, okay? Because default is the target variable. So instead of categories, we call these classes. So no and yes. So whether the person defaulted or not. And as you can see here, we have, let's say, 97% of people who did not default, right? 97% of people did not default. 3% of people defaulted, okay? This is an unbalanced data set because the no class is much more frequent than the yes class. So 97 versus 3%. So it's an unbalanced data set. And as you will see, when we apply the classification solution in a second, the performance is not very good, especially for, or actually exclusively for the yes class. So the performance for the yes class is not good. Okay. And then as you will see, once we change the probability threshold, things improve. All right, perfect. So here, what I'm doing, guys, this is kind of optional. You don't have to do it, but I think it's a best practice, if you will. The thing is that in scikit-learn, it's okay to have these 2 classes, no and yes. But in many other applications outside scikit-learn, the classes should be 0 and 1. So instead of no and yes, it should be 0 and 1. So as a kind of best practice, I always transform this to 0 and 1. Okay. Again, you don't have to do it. It will work fine like this in scikit-learn, but as a best practice, let's just, go ahead and do it. Okay. Notice that what I'm doing here is I'm saying, all right, so if default equals yes, I want to create a 1. So I want to transform that. I want to return a 1. Otherwise, I want to return a 0. And we are storing all of that back in the same column. Okay. And sure enough, let's run that code cell. Once you take a look at the default column from the default data frame, it's not no and yes anymore. It will be 0 and 1. Okay. Again, not mandatory to do, but a good practice. Okay, perfect. What else? What else? Okay, so another thing I want you to pay attention to is that, as I told you, we have 3 features, right? Student, balance, and income. But student is categorical. It's object data type. Object data type means it's categorical, nominal. Okay. Remember, in both classification and regression, we cannot have categorical features. We must transform categorical features into numeric ones, and I'm doing that by applying dummy coding. Okay. I am applying dummy coding using the get dummies function on the student column from the default data frame to convert it into a dummy. Okay. And I'm kind of creating a new data frame with that dummy. So default df dummies, that's the final data frame we're going to use. Okay, let's take a look. And in that data frame, notice that again, we have, default, balance, income, but we don't have student object type anymore. So we have student yes, and it's Boolean. Student yes is a Boolean column that will be true when the person is a student, and it will be false when the person is not a student. Okay, and now you may be wondering. So like maybe you thought we needed to have like a numeric data type in a year of float. Well, not really. Boolean is okay. So internally, scikit-learn will work perfectly fine with Boolean, okay? Because internally, truths will be treated as one, and then false will be treated as zero. We can transform it if you want. So we can transform this into an integer where true is one and false is zero, but we don't have to, okay? So scikit-learn will work with this Boolean fine, okay? All right, so we're ready. So we don't need to do anything else. So at this point, we are ready to obtain the classification solution. And the classification algorithm I'm going to apply is logistic regression. So I'm going to obtain a classification solution using logistic regression, and then I will show you that the performance is not good, especially for the positive class, okay? But before doing that, I'm going to split the data because what I want to do is I want to use the training data to train the model, to train the classification solution, and then I want to evaluate the performance of that model on test data. So that's why I am splitting the data. To split the data, I usually like to do these two steps first. So I like to store in a variable all the features. Okay, that's what I'm doing here. So here I'm dropping from the data frame default. Basically, I'm kind of keeping all the features, and all the features will be stored in that variable. And I like to create a variable specifically for the target. Okay, for default. Okay, and once I do that, I go ahead and do the split. To the split, I apply the train test split function, pass these two variables as argument. The third argument is the test size. 0.20 means I want to use 20% of the data for testing and 80% for training, okay? So 80% for training, 20 for testing, random state equals 1. I'm basically setting the random seed to 1 because I want everyone who uses this notebook to get the same result. So this controls the randomness so that everyone that uses this notebook get the same result. And the last argument is kind of optional, but I kind of like to do it as well. I like to use it as well. Stratify set to the target variable because I want the target variable to have the same class frequency in both training data and test data. Okay, so let me repeat that. So I want the target variable to keep the same class distribution it has in the whole data set in both the training data and the test data. In other words, I want the percentage of no and yes to be the same in the whole data set, not necessarily the same, but similar. I want the percentage of no and yes to be similar in the whole data set, the training data set, and also the test data set. Okay, and to that I set stratify to the value of the target. Again, optional to do, but kind of a best practice. All right, and notice that the output from train test split will be 4 objects. Okay, this is a data frame. Xtrain is a data frame with the features for the training data, for the training observations. So training observations with all the features. This would be the test observations with all the features. This would be the training observations with the target, and this would be the test observation with the target, okay? All right, so let's run that. And now we are ready to fit our classification solution. And as I told you, I'm going to fit a logistic regression model. To keep it simple, I will just use the default hyperparameters from the logistic regression algorithm. Okay, so in scikit-learn, you can tweak the logistic regression algorithm. You can tweak many hyperparameters for the logistic regression algorithm. I'm going to use the default ones. Okay, I want to mention a couple of the hyperparameters that you should be aware of. Okay, but again, I'm using the default ones. Okay, the first hyperparameter is L1 ratio. The default value for that hyperparameter is zero, which is the one I'm using. And when you use zero, that means that instead of L1, you want to use L2 regularization. Remember that we have two types of regularization, L2 regularization, L1 regularization. By setting L1 ratio to zero, it means I'm using L2 regularization, okay? All right. The other hyperparameter to know about is C, and I'm using the default value, which is 1. C is the inverse of the regularization strength. And what you should know is that smaller values means stronger regularization. 1 means kind of intermediate level regularization, if that makes sense. So it's not too strong regularization, but not too weak either. So it's kind of an intermediate level of regularization. Okay, that's the one I'm going to use. And class weight, I'm gonna use the default value, which is none, and none means that both classes will be given the same weight. So both classes, no and yes, will have the same importance in the learning process. Okay. Again, guys, you can tweak some of these hyperparameters to change performance. I'm gonna go with the default ones, okay? Because my purpose here is not to tweak hyperparameters, but actually to tweak the probability threshold. Okay. All right. Perfect. So here I am defining the logistic regression model. So I'm not feeding the model yet, just defining it. Okay. And to define it, I'm going to use the function make pipeline because this is the thing. Remember that it's very important that if you apply a machine learning method that applies regularization, and in this case, we are applying L2 regularization, you should standardize or normalize the features. Okay, either standardize or normalize the features. Okay, it's very important to do that. So one easy way of accomplishing that in scikit-learn is by using a pipeline, like using the make pipeline function. With this pipeline, we're going to be able to standardize the features first and then apply logistic regression. Okay, so, and that's what I want. So I want to standardize the features and then after that apply the method, apply the machine learning method. Okay, very easy to do using the make pipeline function. Okay, so let's define the model. Let's define the model, and notice that for logistic regression, I'm just using empty parentheses, meaning like that means that I'm just using the default hyperparameters. Okay, so we define the model, and now we feed the model to the training data. Notice that we are passing the training data, so features and then the target. Okay. Okay, so we train the model and notice that this is telling us that first the data was standardized using the standard scalar function and then logistic regression was applied. Okay, that's what I wanted. Now, what do we do now? Well, let's use the train model to predict the test data and see how the performance of that model is. Okay, is it a good performance, bad? Okay, all right. So here we're using the model and we are invoking the predict method on the test data. So we are invoking the predict method on the model on the test data. And what I'm doing is I am storing the predictions, okay, in that variable. Y test predict, because we are predicting the target Y for the test data. So that's why Y test. But these are the predictions. So that's why it's called Y test predict. Okay. You can use a different name, but I think that's a nice name. Okay. All right, so let's run that. And then a couple of things to remember, guys. Maybe you didn't know, but that's why you're here. Anyways, when you invoke the predict method in scikit-learn, scikit-learn uses a probabilities threshold of 0.5. So remember that probability threshold 0.5? Well, when you invoke predict, and that's something that you need to know, when you invoke predict, 0.5 will be used as the threshold, okay? And that's something that you can change, but in principle, it's 0.5. Okay, so um, the predictions stored in that variable are obtained using a threshold of 0.5. Okay, cool. Now what I'm going to do is I just want to check, okay, are these predictions good? In other words, are these predictions close to the actual values? Well, I'm going to do two things. I'm going to obtain a confusion matrix. Um, And then I'm going to obtain a classification report. In the classification report, you're going to be able to see all the metrics, recall, precision, the accuracy, okay? But first, let's go ahead and obtain a confusion matrix. And remember, in a confusion matrix, we can see the actual values of the target and the predicted values of the target. This first row will be all the information for the zero class, and this second row will be the information for the one class. And notice that here we have the number of true negative, false positive, false negative, true positive. Okay, and notice that the performance for the zero class seems to be pretty good. Okay, because we have only a few false positive, but the performance for the one class doesn't seem to be very good because we have a lot of false negatives. Okay. And we can confirm that by obtaining the classification report. And when we see the classification report, again, the classification report gives us the precision for each class, the recall for each class, the F1 score for each class, and also the accuracy. This right here, that right there, 0.97, 97% is the overall accuracy, okay? Anyway, so all right, the overall accuracy seems acceptable in principle. 97% seems okay. The recall, let's focus on the recall for now. The recall for the zero class is 100%. It's not really 100% because here we saw that we have 9 false positive, but if you round to 2 decimal places, it will be 100. Okay. Actually, the recall is for the no class is 0.99 something. Okay. But rounded to 2 decimal places, um, it's 1. Okay. Anyway, so the recall for the zero class is very good, but notice the recall for the one class, 36%. Okay. And we saw that we have more false negative than true positive. Okay. So that's why the recall for the one class is so low. 36%, that's too low, guys. So we cannot be satisfied with this solution because, yes, the recall for the zero class is great. The overall accuracy seems to be also good, but the recall for the one class, 36%. That means that this model only detects 36% of the defaulters. So among the people who are going to default on their balance, it only detects 36% of them. Very, very low. Okay. So we need to do better. One of the dials that we can play around with to improve this is changing the probability threshold. Okay. And that's what I'm going to show you now. How can we change the probability threshold to improve performance specifically for the one class? Okay. And usually what you want to do with the probability threshold is to reduce it. So from 0.5, you reduce it, okay? Because the uh, positive class is the least frequent class, because the positive class is the least frequent class, and you want to improve the performance for the positive class. What you want to do is you want to reduce the probability threshold, okay? And that's why in this case, that's what I'm going to try to do. I'm going to try to reduce the probability threshold, okay? Now, remember that we need to match the probability threshold with this. So predicted probability returned by the model. So now I'm going to show you how to retrieve that predicted probability, store that probability in a variable, and then kind of set up that inequality with a different value instead of 0.5. Okay. So how do we get the predicted probability returned by the model? Well, there is a method, and that's what I'm kind of explaining here. There is a method called predict proba. That predict proba will give us the predicted probability returned by the model. Okay. And let's take a look at that, guys. So notice that if we invoke predict proba on the test data, on the model, so this is the model, and then we invoke predict proba on test data, we get this. Okay. Notice that this is a two-dimensional array, and the number of rows in that two-dimensional array is the number of rows in the test data. How many rows we have in the test data? So that's the same number of rows in that array. And we have two columns. We have two columns. One column is the predicted probability for class 0, and the other one is the predicted probability for class 1. Okay. And if you ever want to confirm, like, oh, how do I know what is the first class and what is the second class? You can always invoke classes. Invoke the attribute classes on the model, and then you will see that the first class is 0 and the second one is 1. So that's why I know that this is the predicted probability for class 0. This is the predicted probability for class 1. More specifically, what does this mean? For example, the first row. The first row is the first test observation. So for the first test observation, the probability that the first test observation belongs to class 0 is this. And the probability that the first test observation belongs to class one is this. And same thing for this. So for the second test observation, the probability that it belongs to the zero class is this. The probability that it belongs to the one class is this, okay? What we need to store and retrieve is the probability that each test observation belongs to the positive class. That's the one that we need to retrieve, okay? So we want to retrieve the probability that belongs to the positive class. So we need to retrieve the second column, okay? And that's what I'm doing here, guys. So I'm kind of repeating the same thing, predict proba X test, but I am retrieving the second column. Index one for the column. Index one means the second column, right? And notice that I am storing that predicted probability for class one in this variable. Probability target is one. So this is the probability that the target is one for each test observation. And sure enough, now we have a one-dimensional array only, and this will be the probability for each test observation of belonging to the positive class. Okay. Now, once we have this, we can play around with the probability threshold. What I'm going to do is I'm going to change the probability threshold to 0.4. How do I do that? Very straightforward. I set up this inequality. So if the probability is greater than whatever I want, in this case 0.4, okay, then I want to return a 1, otherwise I want to return a 0. And what I do is I store those predictions in a new variable. Okay, notice that this variable is called y test prediction 0.4 because I'm using a 0.40 uh, probability threshold. Okay, and as you will see, you can play around with this threshold and change it. Okay, but yeah, that's the way you change the probability threshold and come up with new probabilities. I'm sorry, with new predictions. Okay, let's go ahead and run this. And once you have that, you can obtain a new confusion matrix, but using these new predictions, okay? And now notice that in the confusion matrix, kind of see the number of false negative. It has reduced a little bit. Initially it was 43, now it has reduced. Okay, that's good. Good sign. And if you obtain the classification report, well, things have improved a little bit because now the recall went from 0.36 to 0.42, a little bit better. Still not good, but a little bit better. And we still have a good recall for the zero class and a good accuracy, okay? But you can keep playing around. You can say, how about the 0.3? So can I get the predictions with 0.3? Yes. All you have to do is change that. So 0.3, and now you can obtain a new confusion matrix with these predictions, and you will get something like this. So even better, like the number of false negative keeps decreasing, right? As a matter of fact, now you see in the classification report that, hey, the recall for the one class keeps increasing as we reduce the probability threshold. So that's good. Again, this is not satisfactory yet because 52% for the recall for the positive class, 52% sensitivity is not good, but it's moving in the right direction. Okay. Anyways, this is kind of boring, like changing that one by one. So we can generalize this by defining a function. So, and this is what I did. Like, if you want to be kind of speed up this process a little bit more, you can define a function, and that's what I did here. This function basically takes all of these arguments and returns the predictions with the specific threshold that we established. Okay, so it takes a specific model, a specific trained model, so a model that you trained. It takes the data that you want to predict. Okay, train model, the data that you want to predict, what threshold you want to use. Here you can use 0.5, 0.3, 0.4. Okay. Specification of what the positive label is, what is the negative label, and then it will return the predictions with that specific threshold. Okay. So let's go ahead and run that code cell to define that function. And now, guys, you can loop. This is what I'm doing in the next code cell. I'm looping through that. Notice that I'm looping through that. I'm looping through a list, and I'm invoking that function with each element of the list, okay? Kind of to speed up this process. So, and the list that I created here was very small, only four thresholds, but you can have like a more comprehensive list. So maybe you want to check more thresholds like 0.5, 0.45, 0.40, 0.35. Perfect. You can go ahead and do that. No problem. Okay. Here, as an illustration, I just loop through four thresholds. Okay. But the bottom line is that once you have that function, if you run that loop, you're going to be able to get in one output, in one output, all the classification reports for the different thresholds. So like instead of like this, like one by one, right? One for 0.4, one for 0.3. So you can loop through through those thresholds and get the classification report for each threshold, okay? And notice that as we saw earlier, as we reduce the probability threshold, the performance for the positive class improves, okay? 0.42, now 0.52, and even better for 0.420, it's 0.63, okay? So it keeps improving, all right? So that's great. So that gives us an idea that, hey, when we reduce the probability threshold, the performance for the positive class improves. And the performance for the negative class still, let's say, decent. Okay. It still at least seems to be decent. Okay. Because even with threshold 0.2, the probability, sorry, the recall for the negative class, it's still 97%. So it has reduced, but still seems to be decent. Okay. And then the recall for the one class has improved a lot. Are we happy with this recall for the one class? Maybe not. Maybe we want even more higher recall, but at least we are moving in the right direction. Okay. So my idea is to show you that by tweaking the probability threshold, you can improve the performance for the least frequent class. Okay. In case you have an unbalanced data set. Okay. All right. So I'm going to leave you with this now, guys. So this is an even more useful analysis, as I said here. So you can actually come up with a plot showing all of this. So if you don't like this, which I think you should like this because it's a nice summary, but if you don't like this and you want kind of a more graphic output, you can actually obtain uh, the following um, the following chart. I'm going to leave you as a homework, sorry, I want to leave you as homework for you to explore the logic of this code. Very straightforward. Basically, I'm just looping through different threshold, invoking the function, and then plotting in a scatter plot the recall for both classes and the overall accuracy for different thresholds. That's what I'm doing. Plotting in a scatter plot the recall for both classes and the overall accuracy for different thresholds. Okay, but you can go ahead and explore this code by yourself. Okay, but for now, let's go ahead and run it. And one thing that I want to mention is that here I decided to like loop through more thresholds. So I'm going from 0.10 to 0.50 in steps of 0.05. So I'm going to check thresholds 0.10, 0.15, 0.20, 0.25, dot, 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 0.50, okay? Anyway, so let's go ahead and run this code cell, and this is what you get, guys. That's a nice graph where you can see the effect of threshold on recall and accuracy. Notice that the blue dots, first, forget about the blue dots. So first, notice that the x-axis will be the different thresholds. And on the y-axis, we have different performance metrics, three performance metrics. The recall for the yes class, those are the blue dots. The recall for the no class, orange dots. And then the overall accuracy, the green dots, okay? And again, notice that as we reduce the threshold, we can see a trend for the recall for the yes class to improve, to increase. And also we see a slight trend for both the recall for the no class and the accuracy to decrease. So when we reduce the threshold, both the recall for the no class and the accuracy decrease slowly, okay? And then here we can kind of see like, do we see any threshold that give us what we want? Okay. I don't know. I'm gonna just say something as an example. Maybe you want a situation, maybe you want a solution where I'm just making this up. Maybe you want a solution where the recall for the yes class is 70% at least. Let's say you are satisfied with that. At least 70% recall for the yes class, and the recall for the no class and the overall accuracy should be more than 90%. That's the solution that you want. Well, if that is the case, it looks like two thresholds will give you that, 0.10 and 0.15. With 0.15 threshold, we get a recall for the yes class a little bit above 0.70, okay? And the recall for the no class and the accuracy are above 90. So 0.15 will be a threshold that meets those requirements. But also 0.10. 0.10 gives you a recall for the yes class of 75% and the recall for no class and accuracy is still above 90%. Okay, so in that hypothetical situation where you want a recall for the yes class of more than 70% and recall for the no class and accuracy above 90%, with this approach, you'll be able to find two thresholds that meet those requirements. Okay, all right, guys. So that's the idea. So when you have unbalanced data, usually the performance for the least frequent class, which is usually the positive class, will be bad. Okay, and one way, just one way of improving the performance is to tweak the probability threshold and to try a smaller probability threshold. Remember, it's not the only way. You can also try oversampling and other approaches, but definitely one approach that you should keep in mind. All right, guys, that's all for this video. I hope you enjoy. I hope you learn a lot, and I will see you in a different video.